Space is vast, it is full of mystery. One of its most fascinating objects is the black hole. Imagine a place where gravity is so strong that nothing, not even light, can escape. This is a black hole. Black holes are not empty spaces. They are regions of extreme density. They are formed from the remnants of massive stars. Understanding black holes helps us understand the universe's evolution. Our journey into the heart of a black hole begins with the life cycle of stars. Stars are born, they live, and they die. Their deaths can be spectacular events that pave the way for the formation of black holes. Stars are born in giant clouds of gas and dust, vast and ethereal formations that float through the cosmos. These clouds, called nebulae, are scattered throughout the universe, each one a potential birthplace for new stars. The Orion Nebula is a famous example, a stellar nursery where new stars are constantly being formed. Gravity acts as a sculptor, pulling these clouds together, shaping and molding them into dense regions. As the cloud collapses, it fragments into smaller clumps. Each one a potential star in the making. Each clump continues to collapse under its own gravity, growing denser and hotter as it does so. The material at the center of the clump heats up, glowing brightly as it reaches higher temperatures. This hot, dense core is a protostar, the earliest stage in the life of a star. Over millions of years, the protostar continues to gather material from its surroundings, growing in mass and size. It gets hotter and denser, the pressure building up in its core. Eventually, the temperature and pressure at the core become high enough to ignite nuclear fusion, the process that powers stars. When fusion begins, a star is born, shining brightly in the darkness of space. The star shines brightly, radiating energy outward, a beacon of light in the vastness of the universe. This outward pressure balances the inward pull of gravity, creating a stable star that can shine for billions of years. A star's life is a constant struggle between gravity and nuclear fusion. Gravity tries to pull all the star's material inward. Nuclear fusion occurring in the star's core pushes outward. This outward pressure, created by the energy released from fusion, counteracts gravity's pull. This balance is what keeps a star stable. The star's mass determines how long this balancing act can continue. Massive stars have a lot of fuel. They burn through it quickly. Smaller stars are more efficient. They burn slowly and live longer lives. Our Sun is a medium-sized star. It has been shining for about 5 billion years. As a star runs out of hydrogen fuel in its core, its balance starts to shift. The outward pressure from fusion decreases. Gravity gains the upper hand. The core contracts and heats up. This heat causes the star's outer layers to expand. The star swells up to many times its original size. It becomes a red giant. Red giants are cooler than their main sequence counterparts, hence their reddish appearance. Eventually, the star's core becomes hot enough to fuse helium into heavier elements. This process releases more energy, temporarily halting the star's collapse, but this is only a temporary reprieve. Section 5, Supernova, a star's grand finale. This is the dramatic and awe-inspiring conclusion to the life of a massive star. When a massive star reaches the end of its life, it has fused elements up to iron in its core. This process of fusion has been ongoing for millions of years, creating heavier and heavier elements. Iron fusion does not release energy, it requires energy. Unlike the fusion of lighter elements, which powers the star, iron fusion is a dead end. This marks the beginning of the end for the star. The star can no longer sustain the nuclear reactions that have kept it shining for so long. With no more outward pressure to support it, the iron core collapses in on itself. Gravity takes over, pulling the core inward with immense force. This collapse happens in a fraction of a second. The core's implosion is incredibly rapid and violent. The core's temperature and pressure skyrocket. Temperatures can reach billions of degrees and the pressure becomes unimaginably high. The core rebounds with incredible force, sending a shockwave through the star's outer layers. This shockwave travels outward at tremendous speeds. This shockwave blasts the star apart in a cataclysmic explosion called a supernova. The energy released is so immense that it can briefly outshine an entire galaxy. Supernovae are among the most energetic events in the universe. They release more energy in a few seconds than our sun will in its entire lifetime. They can outshine entire galaxies for a short time. The light from a supernova can be seen across vast distances in space. They also play a crucial role in creating and dispersing heavy elements throughout the universe. Elements like gold, silver, and uranium are forged in these stellar explosions and spread across the cosmos, seeding future generations of stars and planets. Section 6. The making of a black hole, gravity's triumph. During a supernova, if the core of the star is massive enough, something incredible happens. The outer layers of the star are blasted into space, creating a spectacular explosion that can outshine entire galaxies for a brief moment. Gravity wins its ultimate victory. The immense gravitational forces at play cause ripples in the fabric of space-time, known as gravitational waves. The core collapses completely under its own weight. This collapse happens in a fraction of a second, transforming the core into an incredibly dense object. Imagine squeezing all the matter of the Earth into a marble. The density would be unimaginable, far beyond anything we experience on Earth. This is the kind of density we're talking about. The matter is so densely packed that a single teaspoon would weigh billions of tons. As the core collapses, its gravity becomes infinitely strong. The gravitational pull is so intense that not even light can escape its grasp. This region of infinite density and gravity is called a singularity. It is a point where the laws of physics as we know them break down. It is at the heart of every black hole. The singularity is surrounded by an area where the gravitational pull is so strong that nothing can escape. Around the singularity is an invisible boundary called the event horizon. This marks the edge of the black hole. The event horizon is the point of no return. Once an object crosses this boundary, it is inevitably pulled into the singularity. Once something crosses the event horizon, it can never escape, not even light. This is why black holes appear black. They absorb all light that comes too close. This is why black holes are black. They are cosmic vacuum cleaners, pulling in everything that strays too near, making them one of the most fascinating and mysterious objects in the universe. Section 7. Black holes, more than meets the eye. Black holes are often depicted as cosmic vacuum cleaners, sucking up everything in their path. This is a misconception. Black holes have gravity, just like any other object with mass. If our sun were to suddenly become a black hole, Earth would continue to orbit it just as it does now. The only difference would be the lack of sunlight and heat. Black holes do have a strong gravitational pull, especially close to the event horizon, but their influence diminishes with distance, just like any other gravitational field. Section 8. Types of black holes, a diverse family. Black holes come in different sizes. Stellar mass black holes are the most common type. They form from the collapse of massive stars. They are typically a few times more massive than our sun. Supermassive black holes, on the other hand, are millions or even billions of times more massive than our sun. They reside at the centers of most galaxies, including our own Milky Way. Intermediate mass black holes are thought to be a stepping stone between stellar mass and supermassive black holes. However, their formation and existence are still under investigation. Section 9. Detecting the invisible, unmasking black holes. Black holes are invisible to telescopes that detect visible light, X-rays, or other forms of electromagnetic radiation. So, how do we know they exist? We detect them through their effects on their surroundings. One way is by observing the orbits of stars near a suspected black hole. The star's movements can reveal the presence of an invisible, massive object. Another way is by detecting X-rays emitted by hot gas spiraling into a black hole. As gas falls into a black hole, it heats up and emits radiation that we can detect. Section 10. Black holes and the universe, cosmic architects. Black holes are not just cosmic oddities, they play a crucial role in the evolution of galaxies. Supermassive black holes, in particular, are thought to influence the formation and growth of galaxies. The energy released by matter falling into supermassive black holes can regulate star formation in their host galaxies. This feedback mechanism helps shape the galaxies we see today. Studying black holes also provides insights into the nature of gravity, one of the fundamental forces of the universe. By understanding black holes, we can better understand the universe itself. Section 11. Conclusion. A universe of mysteries. Black holes, once considered theoretical curiosities, are now accepted as real and fascinating objects in our universe. They are reminders of the immense power of gravity and the incredible processes that govern the cosmos. As we continue to explore the universe, black holes will undoubtedly continue to intrigue and challenge our understanding of the cosmos. They are windows into the most extreme environments in the universe. Their study promises to unlock new secrets about the universe and its origins. The journey into the abyss of a black hole is a journey into the heart of the universe's greatest mysteries.